Today I'm going to go through 3 examples to show you how to do implicit differentiation. Maybe your teacher has gone over it recently in your class, but you're still a little confused. So I'm hoping these 3 examples will clear things up. Now, as you see on the screen here, we have x squared plus y squared equals 9. Now, this derivative is a little different because it's a little more difficult to actually solve for y and then take your derivative. So we can use the chain rule to take the derivative implicitly. So the reason that I'm talking about the chain rule is because that y function is made up of x's potentially, right? So it's an inside function here. So when you take the derivative, you take the derivative of each term separately. So the derivative of x squared would be 2x plus, now here's where that chain rule is. We take the exponent, throw it out front, the base stays the same, so we're gonna still have our y of x. The exponent goes down by 1, but we tack on, we multiply by the derivative of that inside function. So that's gonna be y prime of x. And then in implicit differentiation, you also take the derivative of the right side, all the terms in the entire equation. So the derivative of a constant is 0. Be careful on that one. Now I'm going to rewrite this so that it looks a little bit nicer. So we have 2x plus 2y, remember that was y to the first power, times, now I'm going to use dy dx here. So that's the derivative of y with respect to x equals 0. So we're real close. We want to isolate that dy dx, and that'll be our derivative. So I'm going to move that 2x to the other side by subtracting it. 2y dy dx equals negative 2x. If you divide by 2y on both sides, you're going to get dy dx. In other words, the derivative is negative x over y. Negative x over y is the slope of the tangent line on this graph. Now, do you remember what kind of graph this is? This is a circle, and I have a picture of it on the next slide. Here is the picture of x squared plus y squared equals 9. And remember what we just figured out is that the derivative, I like to call that the slope machine because it can tell you the slopes of all the tangent lines on this graph. This is not a function. Remember, it fails that vertical line test, but we can still find slopes of tangent lines. It's just we need more information to do it. Like if I want to know the slope of the tangent right there, I'm going to have to use the x coordinate and the y coordinate. So it looks like it's about 2.2, I would say. So if you plug that into our slope machine, our derivative, we end up seeing that we get negative 2 over 2.2, which is about equal to negative 1 or so, right? And that looks totally right, doesn't it? There we go. There's a line that's going down and to the right at about a slope of negative 1. Now, if we come over here to this point right here, I'm just picking a point that I thought might be useful for us to analyze, 2.1 there. We take the opposite of the x coordinate and divide by the y coordinate, and that tells us the slope right there. And that's about a slope of 1, isn't it? And you could do the same thing down here. You could do the same thing over here. This would work everywhere. So the derivative is composed of x and y information. It was the opposite of x over y. So that's a really cool thing, is that we can find slopes of tangent lines on graphs that are not functions. So here is the next example. So this looks a lot like a polynomial, right? However, we've got these embedded functions in there. That's the y. It's y of x. So we're going to take the derivative of every single section, keeping in mind we may have some products and quotients along the way. So let's do this. The first term here, when we take the derivative of that, we get 15x squared. So we're taking the derivative of everything with respect to x. So x is our independent variable. Now on this next term, we have a product. So we're going to have to use the product rule right here. So the product rule says we take the first times the derivative of the second. Now what is the derivative of y squared? Pretend like it's the independent variable. What would the derivative of y squared be? Well, we'd throw that exponent up front, the base stays the same, the exponent goes down by 1, but remember, it's actually an inside function. So we have to tack on the derivative, which would be dy dx, tack on the derivative of that inside function. So, and then we have to do the derivative of the first times the second. Remember, we were in the middle of a product rule. So that was that part of it. And we go on to the y to the fifth now. What's the derivative of that? Well, once again, we throw that exponent out front as a coefficient. The base stays the same. The exponent goes down by 1. But remember, that's a y, so we have to put the dy dx right here as well. And then we take the derivative of everything, including that right side. Don't accidentally leave a 9 there. The derivative of 9 is 0. Now, this is a little bit different than the last problem, isn't it? Do you see what's different? We've got dy dx in 2 different places. So the strategy is to group them all together and then factor it out. So watch how this works. I'm going to move the 15x squared to the other side. I'm also going to move the negative y squared to the other side because neither of those had a dy dx attached to it. So now I'm going to rewrite the left side. So negative 6xy dy dx plus 5y to the fourth dy dx is all equal to negative 15x squared plus 3y squared. Remember what I said a moment ago. We're going to factor out the dy dx. Both of our terms have a dy dx, so we can factor it out. It's basically a greatest common factor here. So there it's out now, and what's left behind on the inside would be negative 6xy plus 5y to the fourth, and on the right side we have negative 15x squared plus 3y squared. Do you see how we're isolating that dy dx? Now it's only there once, and we can divide both sides by negative 6xy plus 5y to the fourth. Divide it there, negative 6xy plus 5y to the fourth. A lot of writing here, right? And that would be your answer. That's your dy dx. It would be, I'll write it one more time, negative 5x squared plus 3y squared all over negative 6xy plus 5y to the fourth. There's your answer. That's the derivative, that's the slope machine for all the tangent lines on this crazy graph that was the original problem up top. The last example I'm going to do has an exponential in it. So on one side is this y squared, but on the other side we have base e. And do you notice what's going on up there in the exponent? Yes, that's a product. We're going to have to use the product rule when we take the derivative of that inside function. Remember, the derivative of e to the u power is e to the u, so the exponent stays the same, but then you tack on the derivative of that inside function. That's called the chain rule. So the derivative of e to the 5xy would be e to the 5xy. But we're going to tack on the derivative of that inside function, the 5xy. So that would be the first times the derivative of the second, that would be the dy dx, plus the second times the derivative of the first. Now the second is y, the first derivative would be 5, so 5y. So that's the product rule, and that was the chain because the inside function here was 5xy. Now on the right side, we're going to take the derivative. We throw that exponent out front, and the base stays the same, but don't forget, y is actually, we're going to think of that as a function. So we're going to put a dy dx right there with that term. Now the only way we can isolate those two dy dx terms is to do the distributive property on the left side, do the distributive property, and carefully rewrite it. So here we go, 5x e to the 5xy power dy dx on that first arrow, and then the second arrow would be 5y e to the 5xy power again. And I'll rewrite the right side. So we have two dy dx's floating around in this problem, so we're going to bunch them all together on one side. So I think I'm going to minus 5x e to the 5xy dy dx. From both sides, I'll just write it off to the side right here, try to save a little bit of time. E to the 5xy dy dx. Now we factor out that dy dx. We've got two of them, so it's sort of like a greatest common factor here. We factor it out on that right side. That leaves behind 2y minus 5x e to the 5xy power. All of that equals this term right here, so that's 5y e to the 5xy again. And then all we have to do is divide by that parenthesis on both sides. We're going to divide by 2y minus 5x e to the 5xy power. And we have our final derivative. There you go. dy dx would equal this right here. All right, if you found this video useful, I really hope you'll like and subscribe, as well as leave your comments down below. I always enjoy hearing from you. All right, until next time.